for the session, we have with us Professor Ananya Ghosh Dastidar, ma'am. Ma'am is the professor in Department of Business Economics, which is at present the Department of Finance and Business Economics, South Campus, University of Delhi. Ma'am has done her MA, MPhil, PhD from CESP JNU, New Delhi. Ma'am has been teaching and has a research experience of more than 25 years. Her areas of research and teaching include international economics and the economics of development, in particular, the problem of poverty and income inequality in developing countries. Her subject expertise is in areas of macroeconomics, econometric methodology, and Indian economics. Ma'am has contributed a number of research articles in various Indian and international journals and has a few research-based books to her credit. Ma'am has mentored and guided a number of research students, both at the PhD level as well as session. Really, it is always like that, ma'am. Whenever we are requesting ma'am for the session, ma'am is always there for us. Thank you so much, ma'am. Over to you now.
Thank you. I'll just share my screen.
Yes, ma'am.
Just one second. Yeah.
Ma'am, your screen is visible, ma'am, and you're audible.
Okay, thank you. Thank you, Dr. Anjali. Thank you very much for that kind introduction. And very good evening to all the participants. I'll get started now. And what I'll talk about is give you an introduction to the multiple regression model and maybe some issues which might help you as you work with multiple regression models. So that's going to be the focus of my talk today. So very, I would like to really thank the Ramanujan College and the Indian Accounting Association for inviting me here. And thank you all of you for being here on a Sunday evening to attend the lecture. Okay, so I'll get started with by giving you a brief of what all I'm going to talk about. Okay, so before I start talking about the multiple regression model, I'll give you a very brief introduction to the two-variable ordinary least squares model, and then come over to the multiple regression model, and I'll be using a lot of practical applications to demonstrate my points. So in particular, this is what So this is what I plan to do. Start with the two-variable ordinary least squares regression model. And I'll start with some examples. Some examples where I take different sets of dependent and explanatory variables and really talk about the interpretation. How is it that you interpret the results once you have got some regression lines going? Okay. So in a way, I'm kind of working backwards. I'll start with some scatter diagrams, regressions, talk about interpreting them, and then go over to the technicalities, a few technicalities, in particular the model assumptions, and really use an example to differentiate between actual data, between the model predictions and the least squares residuals, because these will have an important role to play in what I talk about when I introduce the multiple linear regression model. So that will be the next thing. As I discuss the multiple linear regression model, I'll talk about the assumptions, a few implications of the assumptions, and then talk about how the coefficients, how the interpretation of coefficients differs between the two-variable and the multiple regression models. and then talk about a few model diagnostics, in particular the R squared and the adjusted R squared. The adjusted R squared, which has special meaning, significance in the context of multiple linear regression. Discuss the problem of omitted variables bias, and discuss various types of hypothesis tests that we can carry out in the context of a multiple regression model. So that's roughly going to be what I'll talk about in the first 1.5 hours. And also I hope to touch on the problem of multicollinearity. And thereafter in the second session, I plan to talk about models with dummy variables. And if we discuss all the issues related to dummy variables, then we can come back and talk about some tests and fix for the problem of heteroscedasticity. So that's the plan of the lecture, and I mean the two lectures that I have with you today. And what I'd like you to, yes,
ma'am, before you start, ma'am, I just want to introduce here and mention that we have with us Dr. Rajiv Nayan from Ramanujan College, who is going to be there, ma'am, with you for helping you out through entire 2 sessions. Rajiv, sir.
Okay, ma'am. Namaskar, ma'am.
Yeah, just once.
So he'll
yeah,
be
hello.
there with you.
Hello, Dr. Rajiv.
Yes, ma'am. Namaskar.
Namaskar.
Thank you.
Okay, great. So thank you very much. And what I would request you to do is, if you have questions, in particular, if you have questions which is, which is sort of hindering your understanding of the flow, so please put the question in the chat box. So I'll keep checking, and if there are questions in the chat box, I'll try to take those questions as I proceed. Okay. So that's going to be the plan. Okay. Now, I just wish I could hide this thing on top of the screen. Okay. Well, right. Okay, so maybe it's just going to go away by itself. All right. So first of all, what is the ordinary least squares regression all about? Now, I do understand that many of you are familiar with econometrics, maybe even advanced econometrics, but I'll just take a brief 10 to 15 minutes to run over the 2-variable model. So when we talk about a 2-variable model, we have in mind literally 2 variables, one of which we typically denote by y, which is our dependent variable, and the other is an explanatory variable. And when we use regression, we are essentially fitting a straight line or estimating a straight line relation between these 2 variables. But the straight line is of the form y is equal to alpha plus beta 1x, where alpha is the intercept of the straight line and beta is the slope of the straight line. So the first thing that I want to do is talk about how we interpret the slope. Now, you know, so these are just some basics. Now, you know that when we have a straight line from basic calculus, that beta is the slope of the line. Now, using basic calculus, it means we can say dy dx is equal to beta, or dy is equal to beta dx, right? So dy is basically a small change in y, and dx is a small change in x. Now, suppose I scale this change to 1. Suppose I say, let's consider a unit change or a 1 unit change in x. So suppose dx is equal to 1. Then dy is simply equal to beta. Okay. So basically, that's the first thing about our 2-variable model. When we are fitting a straight line, typically we are interested in interpreting the slope. And the slope represents the change in our dependent variable for a unit change in the independent or explanatory variable. With this introduction, let's now look at some examples. Now, right. So, just one second. Yeah. Right. Now you can see the top of my screen also. Okay. Now, suppose we have the following kind of data. All right. I have some information on prices of houses and their size. Now, one of the first things that we note over here is what is the unit in which this data is measured. So house price is measured in thousands of dollars and size is measured in square meters. So here my dependent variable is price and my explanatory variable is size. So when I run a regression and I so just one sec. When I run a regression and I yes, sorry about that. Yeah. So I plot the two variables in what is known as a scatter diagram. Okay. And then I try to interpret the result that I've got. So the very thing that I have to be mindful of is the units in which my variables are measured. So once I estimate the straight line, which as you can see has a positive relation, it has a positive slope, right? So what is the equation of the straight line? House price is equal to 11.2 plus 0.14 into size. Okay, so I'll come to how we got this straight line a little later. This data has been used to get this straight line. Right now, I'm just asking you to note how we interpret these results. So this is telling us that if the size of a house increases by 1 square unit, okay, 1 square meter, right, then its price will increase by 0.14 into 1,000. That is $140. Okay, I repeat, when size of the house increases by 1 square meter, its price increases by $140, 0.14 into 1,000. Okay, this is how we interpret the slope of the line that we have estimated using ordinary least squares regression. Okay, so this is my first example, and this line is actually estimated using some cross-section data. So cross-section data is basically data that we collect at one point of time and where the variance in the data, so the reason you have different sizes and different prices of houses is basically these pertain to different units. Okay. So that's the basic idea behind cross-section data. Now I've got some more examples of cross-section data and regression lines and how we interpret them. So here I have a different example where I'm looking at firms. And in particular, we are looking at the salaries of firm CEOs and the return on equity on those firms. Okay. So here I'm saying that this amount of salary that the CEO gets actually depends upon how the firm performs, and one parameter of firm performance is return on equity. Now here's a convention. We always put our dependent variable on the y-axis and we put our explanatory variable on the x-axis. So on the x-axis, I have ROE, as you can see, right? ROE is my return on equity. That's measured on the x-axis. And here I have the CEO salaries, and this is my regression line. Now, what is this saying? So CEO salaries are in $1,000 again, and ROE is in percentage. So here the interpretation is if the CEOs, if the return on equity increases by 1 percentage point, the CEO's salary increases by $18,500, 18.5 into $1,000. Okay, so that's the second example. Let's look at yet another example. Now here I have data on wages and years of education. And I'm saying that how much a person earns in terms of wages depends on the number of years of education that he or she has. Now, again, a cross-section data set, and the estimated regression line is of the following type. Wages is equal to minus 0.09 plus 5.4 into EDU, where EDU is the number of years of education and wage is the person's earnings, right? Now, because wage is a discrete variable which takes certain whole number values, therefore you can see the pattern of the scatter is slightly different from the earlier ones, okay? And so for instance, if you look at this gives you the wages that are earned by everybody in the sample who has about 10 years of education. And you can see that it's not just 1 point. There are actually huge variation in wages, even when you fixed education at 10, right? So here we interpret this as an extra year of education increases wages by $5.4 because wages are measured in dollars and education is measured in years, okay? Right. And now one final example, again with cross-section data, where we have, our variables are pertaining to vehicles, cars, okay? So we have two vehicles, two variables. One is the mileage, the miles per gallon that the car gives, and the second is its weight, okay? And here, as you can see, there is a negative relation, and the slope has a negative sign. So it's 39.44 minus 0.006. So what this is saying about the relation between weight and mileage is the following. As weight of a car increases by, let's say 100 pounds, okay? If the weight of a car increases by 100 pounds, then the mileage that it gives decreases by 0.6 miles per gallon, okay? 0.006 into 100, okay? So that's the first, if you like, introduction to variable models and how we interpret them. Now, the basic takeaway from here is please be very, very careful about the units in which your variables are measured, because that is how you're going to be interpreting your results. That's really the basic takeaway from here. Now, when we are using the two-variable linear regression model, what is it that we are doing? We are actually writing an equation of the following kind. Y, which is our dependent variable, is equal to alpha plus beta x plus u. Okay, so what are these creatures? Y is an observable random variable. X is also an observable random variable. You just saw so many examples of Y and X that I just discussed. What are alpha and beta? In the model, alpha and beta are essentially unobservable constants. We don't know what's the relation between Y and X. We know that there is a straight line out there, but we don't know what's the intercept and what's the slope. And the main purpose of regression is to actually estimate alpha and estimate beta. And we just saw several examples of these estimates, numbers which we obtained from the data. Now, how we obtain them is what I'm going to discuss. And what I would like you to notice, to begin with, our model is stating that the relation between Y and X is not an exact relation. There is an inexactness in that relation, right? And that inexactness is captured by this unobservable random variable, which we call the error term. Okay, so the errors or U is an unobservable random variable, which essentially tells you that even when you have fixed your X, even when X is the same, Y can actually take different values. Okay, different values for reasons which may not always be something that you can observe. So for instance, it means in our house price example, it literally means that even when we have fixed the price of a house at 2,000, we can actually get houses that have different prices. That's the inexactness in the relation between a house price and size. Okay, it literally means that even when we have fixed return on equity at 20, we will see that all firms which have return on equity as 20, their CEOs will actually get different salaries, and for reasons that are not always something that we can measure. So U is basically, in that sense, a random error term. You can see here also that if you fix the years of education at 10, right, you'll see that everybody with 10 years of education is not going to get the same wage. They're actually going to get different wages depending on their circumstances, depending on things like their gender and years of experience. And there are so many other things, some of which may be observable and some would be unobservable. So the errors essentially stand for all those unobservable items. Okay. All right, so that's the first, if you like, peek at our simple two-variable regression model. Now, what is the ordinary least squares methodology all about? How is it that we estimate the straight line that we just looked at? So the first thing that we do is to collect a random sample of observations on both the variables. So in each of the previous examples, you saw how I got the data. And then we fit a straight line to the scatter by the method of least squares. Now, what does the method of least squares do? The method of least squares essentially minimizes the sum of squared deviations from the line of best fit. And I just demonstrate to you what I mean by this statement. Okay. Now, once we have got our line of best fit, right, we basically have an intercept and a slope. And the Ols estimators are essentially the Ols estimators for the intercept and slope of the straight line are basically obtained through this method of least squares. Okay, so let's just look at the method of least squares in a little more detail. So here I have a scatter diagram. Now this is a slightly different example where I'm saying that the sales of a firm depends on their advertisement expenditure. So I have advertisement expenditure on the x-axis and sales, which depends on advertisement expenditure, is on the y-axis. Now, when I fit a straight line to this particular scatter, right? First of all, please realize one thing. If I try to draw a line which passes through all the points, then I'm not going to get a straight line. That's the first point. Okay. Now, once you realize that, then notice the second thing, that I can draw so many straight lines, right? There's so many straight lines that I can draw through this scatter of points. Now, what is it about each of those? Well, for each of those, there's a lot of hit and miss. Some of the points, right, which is part of the actual data, some of the points will be on the line and some of the points will be off the line. So the whole question is to choose the best line. So how do we choose the best line? Now, this is what we do by the method of least squares. So suppose I have x over here and I have y over here. I choose that line as the best line, which looks at deviations of the actual points from this line and minimizes these deviations. Okay, so essentially the least squares estimators are chosen by choosing the line of best fit, which minimizes the sum of squared deviations. Now, if you're wondering why these are squared deviations, it's because you're going to have some lines that are above, rather you could have some data points which are above your line and you're going to have some data points which are below your line. So some positive distances and some negative distances. And if you do not square these distances, then it's simply going to you're simply going to lose data because the distances are going to cancel out, right? So therefore, what you do is for each of these distances, you square them and then you add them up. And then you minimize the sum of squared residuals. And what that gives you is the line of your best fit. So I'll come back to this diagram, but let's just see what the methodology involves. So the method of least squares involves fitting a straight line of this kind, y is equal to a plus bx, to a given scatter of observations. All right, and how do I choose choose this line of best fit? That is, how do I choose the slope and the intercept? I simply look at the deviations of the points on the line. So the points on the line are basically a plus bxi, right? And yi's are the actual observations, right? So I look at the deviations of points on the line from the original data points, and I square all those distances. And let's say I'm just calling this thing Z. And of course, I'm summing across them. So I'm adding all of the squared distances, and then I'm minimizing them. So the minimization procedure, again, using basic calculus, involves choosing the best slope and the best intercept. So the slope is B and the intercept is A. So we choose that A star and that B star, which solve these two equations. Okay, del Z del A equal to 0 and del Z del B equal to 0. Right. So these are simply the minimization conditions, which gives us this particular formulae for the intercept of the line of best fit and for the slope of the line of best fit. Okay. So in other words, the intercept is obtained by calculating this as y bar, that's average value of y, minus b star into x bar, where x bar is simply what appears to be the covariance of x and y in the numerator and the variance of x in the denominator. So this is what you obtain once you have obtained once you solve for this condition of minimization. Okay, so that's what the method of least squares involves. It essentially involves calculating the slope and the intercept using these formulae, which is coming out of the minimization procedure. Okay, minimizing what? Again, to repeat, minimizing the sum of all these squared deviations from the line of best fit. So this is my y, and this is the point which is on the line, which is called my y hat, and these are my residuals. So the residuals are simply the difference between the y's and the y hats. So we'll just see this with an example. All right. But before that, let me just take you through the Ols estimators. So the Ols estimators, alpha and beta. Okay, I think if there's a question in the chat, I'll just take that. Just 1 second. Yes, that's right. So in multiple regression, we have 2 or more independent variables, not one, certainly. I'll come to multiple regression. I'm just giving you a brief introduction to the 2 variable model, and then I'll come to multiple regression. Yes, okay. Right. So so in the 2 variable model, so let me be very specific. I'm talking here about the 2 variable model before I come to multiple regression. The Ols estimators of alpha and beta, okay, essentially use the least squares, intercept, and slope coefficients. That is, the Ols estimators are calculated using these particular formulae, which just correspond to the least squares, slope, and the slope and the intercept estimators. Okay, so beta hat is simply the covariance of x and y upon the variance of x, and alpha hat, which is the intercept, is equal to y bar minus beta hat into x bar. Okay, and the least squares residuals, right? The least squares residuals, which provide an estimate of the unobserved errors, are calculated as the difference between the actual y's and the y hats. But the actual y's are given by the data, and the y hats are what we get out of the our regression. Now, I think I've shown you a lot of sort of algebra. Now let's see some data. Okay, so I'll use this program called Stata, and please let me know if you can see my screen. Can you see my screen? I have Stata on my screen now. Is that visible?
Yes, ma'am.
Okay, thank you. Right. So I will use this data set, which I was talking about, which has data on wages. So I'll just browse the data set and I'll show it to you. It has data on wages and years of education. Just one. So I'll show you the first 10 observations in the data set. I think that would be clear here. Okay. So these are the first 10 observations where I have for the first person, wages are $3.1 and this person has 11 years of education. So these could be weekly wages. So $3.2 for the second person who has 12 years of education and so on. Now, when I'm using Ols regression in Stata, I use a command called reg, which is the command for regression. And when I first write the dependent variables, I'm saying wage depends on education. And then I write the explanatory variable, I get these results. Okay. So you can see a lot of stuff on the screen. Yeah, I think there's a question on the chat. I just come to that. But let me start by telling you what is it that alpha hat and beta hat, I mean, where those numbers are coming from, okay? So this is the command that I gave in Stata. My dependent variable is wage. And you can see this is my alpha hat, okay? So the coefficients are estimated here. So my alpha hat is minus 0.9 and my beta hat, okay, the coefficient of education is 0.54. Okay, so this is telling me that an extra year of education increases wages by $0.54 or about just more than 50 cents. Okay, so these numbers are obtained using those particular formulae. Now, before I proceed any further, I would now like to draw a difference between y, x, y hat, and the residuals. So we're very clear in our minds what all these characters are. Okay, so I'll just check. There's a question. Could you please use SPSS? I'm sorry, but I am not, I think you're going to have SPSS further down the line, but I will be using Stata. So that's something. I do not use SPSS, okay? But the results would be pretty much the same no matter what package you use. So I hope that won't be a problem. Okay, so now what I'm going to do is I'm just going to obtain the predicted values. Now the predicted values are basically my what I call y hats, or these are all the values which are on the line, right? So how do I get it? So in Stata, I'll just get the commands and then I'll explain it. So I'm just going to call this y hat, okay? Then I'm going to get the residuals as well. So just a second. Okay, then I'm just going to get the residuals, predict. I'm going to call the residuals the u hat. Okay, and now I'm going to show it to you. So I'm going to show you again for the first 10 observations, wage, education. So my y variable, my x variable, my y hat, and my u hat, which is my residuals. Okay, right. Okay, so please pay attention to this. So this is my y, this is my x. Now, what are these y hats? So the y hat is basically nothing but, the y hat is nothing but alpha hat plus beta hat into x. So to see that, let's take the first observation. For the first observation, my y is 3.1. So this person earns $3 in wages, has 11 years of education. But what is my model predicting? My model is predicting that this person is going to be earning essentially minus 9.04. So alpha hat, okay, alpha hat plus beta hat, okay, here's my beta hat, plus beta hat, okay, plus beta hat into 11. Okay, so this person has 11 years of education. So here you can see 5.0501. So this is a point on the line. So in other words, if I were to just draw this for you, what you would get is something like this. So I have here wages, I have here education, okay? I have a scatter, and then I have drawn the line. And for the very first observation, for someone who has, let's say, 11 years of education, so let's say this is 11, right? My model is saying that this person should be earning 5.05, okay, as his wage, but this person is actually earning a lot less. So the first observation is actually somewhere out here, okay? This person is actually earning 3.1. So the residual is basically the difference between y and y hat. So this is my model residual, okay? It's the difference between 3.1 and 5. This person is actually earning less than what my model predicts, which is why I have a negative residual, okay? So just to take you back to my slides and make one simple point, just one second. So just to tell you about my model. So we said that our model has this error term where the error term is basically unobservable, right? That's what we said. The error term is basically unobservable. But once we have some data, once we run the regression, what we have is the actual data, which is the observable y, and we have the estimates. The estimates which are obtained from the model, that is, we also have the y hats, and the difference between the y and the y hat gives us the residuals, okay? So I'll just show you the residuals so far as the theory is concerned. So these are the residuals in theory, okay? This is an actual data point. This is a point on the line, and this is a residual, which is the difference between the actual data point and the fitted value or the predicted value, right? That's one way of looking at it. And when I take you to the actual data, this is the other way of looking at it. So once you run the regression, you have alpha hat minus 0.9, you have beta hat, which is 0.54, right? You use those to generate the y hat, and the difference between the actual y and the y hat gives you the residuals, where the residuals give you an estimate of the errors, okay? It's giving you the part of y which is not being explained by years of education, okay? So that's so far as the residuals are concerned. And if you have any questions regarding the residuals or the predictions, anything, then I suggest that you ask the question now. Okay, then we can take it now. Otherwise, I'll proceed. Yes, I'll just come to the question. Right. Yes, please.
I have a question.
Yes.
Myself, Sahifa. Ma'am, this explanation of
Yes.
this least square regression.
Yes.
This is almost similar to simple linear regression, because there also we have one dependent variable and one.
This is simple linear regression. That's right.
This is simple linear regression
yes,
only.
Yes.
But then in SPSS we have two different. For simple linear regression we get different option for simple linear regression, and I think so it is different for OLS also. So it's exactly simple linear regression only with different name. That's what my question is.
You're asking me what I've done in Stata or OLS.
No, I understood what you have done in OLS, this least square, ordinary least square regression.
Yes.
But then, is it simple linear regression only?
Yes, it is only simple linear regression. So all I'm trying to tell you is that no matter which package you use, whether it is SPSS or whether it is Stata, every time you're using simple linear regression, the coefficients are being calculated using these two formulae. That's what I'm trying to say. Yes.
No, because when we run regression in SPSS, in analysis, under analysis, we get two different commands. One for simple linear regression, and I think so there is a command for
ordinary least square regression also.
Yeah, so simple linear regression and ordinary least square regression are the same thing when you have two variables. Absolutely.
And another question is, as you said that education can be and wages, two different variables measured on two different units. So don't we need to convert them into Z score before doing any further?
No. So here one is your dependent variable and one is your explanatory variable. Your dependent variable is measured in dollars and education is measured in years. So this is not where I have more than one explanatory variable. You simply have two variables which have two different units of measurement. So if you yes.
Two different variables, one independent, one dependent.
And they're in completely different units. Yes, that's
two different
fine.
units. Still we can go ahead with. But
of course.
if there are two independent variables or there are two dependent variables, and if measurement unit is different, say one is measured in dollars and another one dependent variable in dollars and another dependent variable say in kilometers, then do we need to convert them into Z score?
Not necessarily. You can convert them into Z scores. So since you asked the question, let me explain that when is it that you convert it into Z scores and when is it that you don't. So I'll have several examples where I have explanatory variables that are measured in different units, okay? And I have run a regression. So in fact, to just address your question, let me take you to one such regression result. So I'll just take you to the regression result, just a second. And okay. Just give me a moment. Yes, okay. So here I have a model where I'm regressing the, can you see my screen? There's a screen that says LN salary and sales and so on.
Yes, we can see.
Okay, so here you see salary is in thousands of dollars. Sales is also in millions of dollars. And ROE is return on equity and ROS is return on stock. Both of these are in percentages. And I have not converted these into Z scores. So is that wrong? No, it's not wrong because I have to be careful when I'm interpreting the coefficients. So I can't really take a look at this 0.28 and say that, oh, this means that 0.28 is much larger than 0.01. Essentially, these are all being measured in different units. So the variables, the coefficients are not directly comparable. Now, if you convert all of them into Z scores, then you can compare them and say that the larger coefficient is actually having more of an effect on Y. So that's the difference. Am I making myself clear?
Yes, ma'am. Understood. So then Z score is completely optional. It's not compulsory.
No, it's not compulsory. It's optional. It's useful because you see what a Z score. Now, when you're measuring a variable as a Z score, you're basically measuring it as a difference from mean divided by standard deviation. So a unit increase in that variable is basically a one standard deviation increase. So when you're measuring every independent variable in terms of Z scores, you're putting all of them on the same footing because each one, a unit increase is a 1 SD increase. So then the coefficient interpretation becomes, if this increases by 1 SD, by how many SDs will my Y increase? So you're scaling all the variables down to change in standard deviations. And there, if you have a large coefficient, you can say that this is causing more of a change in Y than the other one. So that's the usefulness of Z scores.
I have a question.
Yes, please.
I think whenever we want to see the dispersion or the randomness of this data spread, then only we plot these Z residual and Z predicted value. Is it not so?
Yeah, but I think the lady is not talking about the residuals. She's just talking about the variables. So I have sales, ROE, and ROS in different units. So I can actually run a regression where I've converted all of these into their Z scores. And I regress the Z-score of salary on the Z-score of sales, ROA and ROS. I think that's what she was talking about.
And my question is actually,
Yes.
whether the data meets the assumptions or not? So irrespective of that, we are going to perform this action, whatever you have told us. Is it so?
Well, whether the data meets the assumption or not, I mean, we often check whether, the errors are normally distributed or not, whether they're symmetric. But that's always something that we can check. But in many cases, we just, in most cases, in fact, we just go ahead and apply ordinary least squares regression.
Because in your data, I could see the strength of relationship is very weak.
Yes, that's actually often the case with cross-section regressions. So in cross-section regressions, getting variables with 28%, 27% is not unusual. And what is it that we really care about? What we really care about is, A, are these results robust? So if I try out different specifications, are these results going through? That's one of the things that we care about. Whether they're the correct sign according to the theory, and whether, they are, whether my results are coming out to be significant of the expected sign. Despite, checking things like, whether there's a presence of heteroscedasticity. So since I'll be talking about cross-section data, heteroscedasticity is the main problem, right? So those are the diagnostics that we use.
Generally, we don't find it in any of the research papers. Neither the multicollinearity nor heteroscedasticity is mentioned. So straight away.
Yes, that's true. You just plunge into it. Now, heteroscedasticity, actually, that's something I'm planning to discuss also. Heteroscedasticity has become such a sort of, I would say, it has such a standard fix that nobody tests for heteroscedasticity. They simply implement a fix for heteroscedasticity. Okay, so what heteroscedasticity does is it changes the way in which your error variance is estimated. Instead of being constant, your error variance can be a function of the x's. And if you can take that into account and estimate your variance covariance matrix, then you see it's then life becomes easy in some sense. Then you're kind of living with the heteroscedasticity. So that's why people don't bother to check the presence of heteroscedasticity in research papers. That's my first answer to your question. The second, multicollinearity. You see, in particular, if you're looking at papers in economics, they are not bothered about multicollinearity until and unless it's perfect. So I'm just going to discuss like why perfect multicollinearity is a problem. But why don't we care about multicollinearity otherwise? You see, my Ols estimators, all the properties go through. So my Ols estimators are blue in the presence of multicollinearity. So I don't care about it until and unless it's creating a problem. What problem does it create? Again, I'll discuss that. And you see, in economics, particularly people who work with large data sets, care even less about multicollinearity because with very, very large data sets, you have a lot of variation in your independent variables. And that beats the multicollinearity. So multicollinearity tends to inflate your error variance. But if you have a lot of variation in your x, if variance of x is very high, then that brings it down. That brings down the standard errors. So you don't really care about multicollinearity at one level. And economists have just stopped bothering about it, really. So that's why you won't see these even being discussed in a research paper.
Thank you.
Right. I think there's another question. Okay, thank you. Right. Okay. So now let me kind of, if there are no more questions, let me, I think, it's much more meaningful if we have questions and a discussion than if I just go on. So thank you very much for asking questions. Okay. All right. So I hope the distinction between predictions and residuals is clear. So I'll now continue and I'll now come to the assumptions of the two-variable model, because right after this, I'm going to go over to the assumptions of the multiple regression model and we'll sort of draw the parallels. Okay. So the basic two variable model is this one, y is equal to alpha plus beta x plus u, where there is an inexact relation between y and x, right? And that inexactness is being captured by u. If there was an exact relation, then I'd just say y is equal to a plus bx, period. Which means if you fix x, you get one y. But that's not the case. So even if you fix x, you can sometimes get a higher y, sometimes you get a lower y, which means sometimes you will be positive, sometimes you will be negative, right? So the errors are vital to our assumptions. Now, therefore, all our assumptions are essentially trying to put some shape on the errors, because these errors are unobservable, so we can't see them. And we are just trying to make them well behaved by assuming that they are zero mean and that x is uncorrelated with the errors. So in other words, we are trying to say that we are splitting y into these two parts. A part which is deterministic, which depends on x, that's the alpha plus beta x, and the other part which is random, which is the errors. So these are the two parts of these are the two parts of y. And the assumption that x is uncorrelated with the errors is essentially saying that these two parts don't intersect, right? The deterministic part and the random part, they are basically separate. So there isn't any correlation between the x and the errors. That's a very, very important assumption. So errors are zero mean, x is uncorrelated with the errors. And remember, these are all random variables. So y, x, u, these are all random variables. So we can state formally this assumption that the errors are uncorrelated with the x in the following way. The expected value of the errors given x is equal to 0. All that means is that the average value of the errors is 0, even when you fixed the x. I'll just come to what that means. Now, using this particular assumption number 2, okay, what we can see is the following thing, that if I take expectations of both sides of 1, so if I'm looking at the average, remember expected value is nothing but the average of a random variable. So the average value of y given x is equal to alpha plus beta x. Why can I say that? Because the average value of the errors given x goes to 0. So that's the first thing I can state, that there is a linear deterministic relation between the average value of y and x. So when you are estimating your alpha and beta and you're talking about it, you're essentially talking about a relation between x and the average value of y. What else are my assumptions? By the way, if you have any questions about the assumptions, anything that you'd like me to discuss, please put the question in the chat or you could ask. Okay, so so these random error terms are homoscedastic. Okay, that is, they have constant variance and they are identically and independently distributed, which means that the errors are not correlated between themselves. So there's zero correlation between any two error terms, and each error has the same distribution, right? Which is zero mean and constant variance. Now, what I mean by that, I'll just show you a diagram and it should be clear. Now, another assumption is that x is a constant. Sorry, x is not a constant. Okay, x has to be a variable. Now, here, please note why that is so crucial. Here, this is how I estimate the slope coefficient, right? Now, if x was a constant, then its variance would go to 0. The denominator of this term would become 0. And if the denominator became 0, then obviously, there is no beta hat, right? So therefore, it is very, very important that my x variable should not be a constant. It must be a variable. Okay, because otherwise beta hat would not exist. And finally, we have a classical assumption, which is the errors are normally distributed. So that's another assumption. And I just sort of, very briefly, diagrammatically show you what these mean. So you see, that's why I started with the two-variable model. The two-variable model is the one we use to kind of flesh out some of these points, because these can be drawn. We can show them on a graph. So here you go. Now, just bear with me to understand what this graph is saying. So here I have X, right? This is my dependent variable, okay? So this is my X, and this is my, so this is my independent variable, and this is my Y, okay? This is my dependent variable, okay? And what is this giving you? This is basically giving you the distribution of Y given X. Now, what does that mean? Let me just use the other pen. Okay, so what does that mean? It means the following thing. So you see, along this axis, X is increasing. Along this axis, Y is increasing. Now, suppose I were to take X as given, right? X is a random variable. So I have to treat it as though it were a constant. Suppose I say that X is equal to X1. So for my wage education example, it's like saying, let's look at everybody who has 5 years of education. That's X1. Then what is this capturing? This is basically capturing this particular curve, which is giving you the distribution of education, the distribution of wages for all those with 5 years of education. Okay, so that's the point. So let me kind of call this 1. So 1 is a curve which gives you the distribution of education, the distribution of wages for everyone with X1 years of education. Let's say X1 is 5. Now, what about 2? 2 is giving you the distribution of wages for everybody with 10 years of education. Now, look at one thing. These curves have a center. That's the average value of income. So basically, the average income for all those with 5 years of education is this. Okay. The average value of all those with 10 years of education is this, and it's higher because Y is increasing in this direction. Now, let's say this is 15. The average wage of people with 15 years of education is this. Okay, so it's given by this curve 3, and clearly you can see that average education is increasing with, average wages are increasing with years of education. Okay. And the centers of these curves are picking up these average values, so that what the regression line is doing is essentially the following thing. The regression line is basically passing through these averages. Okay, so this thick line that you can see is what we are estimating. Okay, when we are estimating OLS regression or simple regression. Now, a couple of things here. First of all, why is it that we have a distribution even when we fixed X? Why is it that we have this whole distribution thing, right? Even when X is fixed, you actually have wages that would be low versus wages that would be high. That's because of the errors. That's the first thing. Now, the errors are mean zero. Where does that get picked up? These are all symmetric distributions. So you're saying that there are about as many people who have more than average education as there are people who have less than average education. You have as many people who have higher wages than average wages and as many people who have less than average wages when you have fixed the years of education. So the symmetry of the curve is what's picking up your assumption about the error terms being mean zero. They're absolutely symmetric around the average, just as many above as below. Now, what about our assumption of homoscedasticity? If you look at these 3 curves, 1, 2, and 3, each of these have the same variance, right? They're identical. That's what it means to say that the errors are homoscedastic. The errors are mean zero, explaining the symmetry, and you have a distribution in the first place because of the errors. Otherwise, you would have a point. Everybody with X1 years of education would only have Y years of Y amount of income. That's not the case. You have a distribution because there are these random errors, and these random errors are mean zero. They're symmetric. That's giving the curve its symmetry, and the homoscedasticity is reflected in all of these 3 curves having exactly the same variance. Okay. In addition, you have the assumption of normality. Now, where does the assumption of normality show up? The assumption of normality shows up right here. Okay, just one second. Yeah. Okay, so each of these are normal distributions because the errors are normally distributed. So Y is normally distributed, and here you have these normal distributions. And the regression line you're estimating is essentially passing through all these points, right? So I just wanted to kind of sort of relate the assumptions to this particular diagram because I think it clearly brings out certain conceptual perspectives. So now let me move on and now finally introduce a couple of more things, right? Now you see, take a quick look at my model once again. I keep showing it to you. So here, Y is a random variable, X is a random variable, and the errors are a random variable. So the randomness in the Y is getting picked up in the errors. What does that do? You see your beta hat and your alpha hat, which are functions of the X and Y, also therefore become random variables. So in some sense, they have a dual existence. Okay. So when I'm referring to these formulae, beta hat is called an estimator. Okay. So the estimator is basically talking about this formula. Alpha hat is Y bar minus beta hat X bar. This formula is the estimator. And the estimator is a random variable. Where is the dual existence? You see, when I have some data, such as this, you can see my screen, you can see the data. Then you see, again, I have alpha hat and I have beta hat. Now, these are not random variables. These are numbers. So these are estimates. But how did I get these estimates? I got these estimates using those estimators. Those estimators, which are random variables, because if you use another data set on wage and education with the same estimators, you're going to get different estimates. Random variables take different values with different probabilities, right? So the formulae are random variables because they're functions of random variables, but for any exercise, the numbers that you get are just plain numbers. They're estimates, okay? So this is something that you have to remember, because these, there being estimators, confer certain properties. And those properties are actually known as the Gauss-Markov theorem. All right. So I'm just going to state it. I'm not really going to it in much depth. So alpha hat and beta hats have certain statistical properties. And what are those? So they are the best linear, unbiased estimators of alpha and beta. So remember, alpha and beta are just numbers that you don't know, right? So you're using these formulae, alpha hat and beta hat, to estimate them, and you're getting estimates with any particular sample. And these are the best you can do because these are estimators which have the least variance. So remember, random variables have probability distributions. So alpha hat and beta hat have probability distributions which have the least variance, and in that sense they are best. They're linear because they're linear functions of the X and Y, and they're unbiased. Now, what does being unbiased mean? It literally means that the average value of alpha hat and beta hat, right? They lie, sorry, this is getting messed up. So the average value of alpha hat and beta hat, okay, lie on the parameters that they're estimating. So that's the whole thing about unbiasedness. So if you look at the average value of beta hat, it is equal to beta. If you look at the average value of alpha hat, it's equal to alpha. So in other words, if I were to draw the distribution of, let's say, beta hat, right? So I have beta hat over here. I have the probability distribution of beta hat over here. Okay, then I would get a normally distributed curve like this. Why normally distributed? Because errors are normally distributed. So Y's are normally distributed. The beta hats are normally distributed. And where is the center of this distribution? The center of this distribution is at beta. Okay, that's what it means to say we have unbiased estimators. right? So these are certain statistical properties. They come out of the fact that these are random variables, which in turn come out of the fact that the errors are random, the y's are random, the x's are random, and so on. Okay, so now having kind of taken you through this, let me just talk about one more implication of what it means to say that, you know, these are random variables. Just a second. So, oops. Yeah, okay. Right. So you see, this is the example. Let me show it to you on my Stata screen. So you see, there are these standard errors which are also reported out of as part of my results. What are these standard errors? These standard errors are basically the variance of the they're coming out of the variance of these random variables alpha hat and beta hat. Okay, and these standard errors are used to test hypotheses about these coefficients, and those hypotheses are being captured here. So these are the T statistics which are testing hypotheses about the parameters. They're testing the hypothesis that beta is equal to 0 and alpha is equal to 0, and so all of this, the fact that you're able to do these hypothesis tests, the fact that you're talking about standard errors of the estimates is essentially coming out of the fact that you're dealing with random variables. Okay, so very quickly to kind of take you through. So basically alpha hat and beta hat being random variables, they have these distributions. Beta hat is distributed normally with mean beta and its variance beta hat, and you know its variance is var beta hat, where var beta hat has this particular formula. Okay, and var alpha hat has this particular formula. So I'm just showing you the formula to tell you that, you know, you kind of estimate variance of beta hat, variance of alpha hat by getting an estimate of sigma square. The sigma square is your is the variance of your errors. Okay, so once you've got an estimate of all of those, you've got an estimate of the variance of beta hat, you've got an estimate of the variance of alpha hat, and square root of those gives you the standard errors of the OLS slope and intercept estimators, which in turn are used for hypothesis testing. So here I'm not really kind of going into details of any of this because I'm assuming that you have some basic background of hypothesis testing, but if you have any questions, please ask. So in particular, for tests concerning beta, right, the test statistic, which is again a random variable, has this particular form. It is beta hat minus beta upon the standard error of beta hat, which has a t distribution. So in other words, if you want to test the null hypothesis that beta is equal to 0, okay, then you simply plug in beta equal to 0 over here, and your test statistic gets this particular form, beta hat upon the standard error of beta hat. So this very important test statistic or the t statistic is always reported with our standard regression results. So I'll just take you there and show this to you. So if you look at this particular t statistic 10.17, how are we going to get it? Well, we shall simply divide this coefficient, okay, and divide it by the standard error, okay. So what you get is 10.166 and 10.17. So that's exactly what this t-stat is. And this has a p-value of 0, which means that you're strongly rejecting the null that beta is equal to 0, okay. So this t statistic is giving you a test for this particular hypothesis that the estimated coefficient, that is beta hat, you're using that to test the null hypothesis that the original beta is equal to 0, whether that's true or not. Okay, so I realize this is a real quick kind of discussion on hypothesis test. But if you have any questions at this stage on either p-values or t-statistics or on hypothesis test, you could put it in the chat box, or you could ask now. Okay. Because now I'll just move over and talk about the multiple regression model hereafter. Yeah, okay. Yeah, a few other things. So you see, what I'm trying to do is the following thing. I'm trying to kind of flash some of the basic stuff that you see with the two variable model, so that, you know, we're kind of up with the basics. So one of the things that you see is the model R squared. Now, what is the R squared? The model R squared is nothing but, it tells you what percentage of the total variation you observe in wages is actually explained by your model. In what sense? So basically, look, you have two variables. You have Y, which is what you started with, which are your wages, right? And then you have the estimated value, which is your Y hat, right? So Y hat is what your model is predicting. So this is simply alpha hat plus beta hat into education, right? So what is your R squared? Your R squared is basically the variance of Y hat. Y hat is what your model is explaining upon the variance of Y. So you see, it's given right here in the ANOVA table. Sums of squares is just another expression for variance. So if you look at your model sum of squares, this is basically the variance of Y hat. And if you look at what percentage that constitutes of your total variance, the total variance in Y, then that's just about 16%. Okay, 16.5%. So that's that percentage of the total variation of wages is actually explained by education. So R squared is another sort of important flag point so far as our two variable model is concerned. Okay, not just the two variable model, we see that for the multiple regression model, we'll be talking about the adjusted R squared. So, right. Okay. So, so we have some, I mean, you can actually see that for any model, the R squared is the square of the correlation between the dependent variable and the predicted values. So it's a square of the correlation between Y and Y hat. But then only in the two variable regression model will you see that R squared is actually the square of the correlation between Y and X. Okay, that's only true for a two variable model. Okay, so finally we're here. All right, finally I'm talking about the multiple linear regression model. So I'll start with the assumptions and of course the basic difference. The basic difference between your two variable model and the multiple regression model is that in the multiple regression model, you have one dependent variable, but you have more than one explanatory variables. In particular, I'll say that there are k explanatory variables, beta 1 to beta k, and one constant term. So basically, you have k plus 1 unknown parameters. In a multiple regression model, there are k plus 1 unknown parameters compared to only 2 for the two variable model. Now, again, you're assuming that the errors are zero mean, they are homoscedastic, they have constant variance, they are identically and independently distributed, there's zero correlation between the error terms, and you are also assuming that, right, you're also assuming that the errors are uncorrelated with the x's. Okay, so that's another important assumption which we earlier made for the two variable model. Same assumption carries over here. So with all these assumptions, you can write the model in the following form: that the average value of the y given the x's has this particular form. Okay, that it is the average the average value of y is alpha plus beta 1 x1 plus beta 2 x2 plus beta k xk. Okay. Again, none of the x variables is a constant. Okay, yeah, there's a question. I'll just come to that. We say that there is no perfect correlation between the x's. This is a new assumption. And also, we say that the errors are normally distributed. So most of the assumptions are the old assumptions we saw in the two-variable model. The only new thing is really this one. We are now saying that there should not be any perfect correlation between the explanatory variables. Okay, that's a very important assumption which we now bring in. What is homoscedastic? Okay, homoscedastic. I'll just come to what is homoscedastic. Okay, so before I end this session, I'll come to it. But let me just stress on this, that there is no perfect correlation between the x's. That's right. So that's one of our assumptions, and this assumption was earlier not there because we had only one x, right? Now, why is this so important? You see, why this is so important has to be understood by looking at the following thing, that we can actually write our multiple linear regression model in matrix notation. All that involves is the following thing. Okay, so just look at the following thing. So let me just write out a model where I am regressing wages on years of education, on years of experience, okay, and on tenure, where tenure is the number of years that a person has been with the current concern, okay, current company. And let's say I also have a dummy variable called female, right? Sorry, it's wage. It's not wages, it's wage. So yes. So you see, when I'm saying I can write my multiple regression model in matrix notation, I just have something like this in mind. Okay. So this is my y. This is my x1. This is my x2. This is my x3, and this is my x4. All right. So you see, we stack, when we are looking at the data, we stack the data observation by observation, right? So you have all the y's stacked, right? I just have 10 of them for you. And if you look at the first row, as if this is the first row of the matrix, then you're talking about the first observation, which pertains to the first individual. The first observation, so the first person has 3.1 years, $1 of wages, 11 years of education, 2 years of experience, 0 years of tenure, and is a female. Okay, that's what this means. So if you keep this in your mind, and if you then look at what I'm talking about, then perhaps it will be clear what it means to write the model in matrix notation. So your y's are simply stacked, and they are a column vector. They're just like a column. So the betas, of course, have to be written theoretically, and they are also a column vector because they are actually picking up each of these rows. Okay, and the errors are also a column vector. So you're writing your model in this particular way, where X is a matrix. Now look at this. This is X into beta. So X into beta is simply telling you that this beta vector is multiplied with this X matrix. So the first column is multiplied into the first row. And the reason you have a column of ones is because you have to pick up this alpha. The model has an intercept. So it's alpha plus beta 1 x11 plus beta 2 x22 plus beta k xk1. And that's how you can write your model. So I hope the X matrix, what it represents, is clear, right? Yes. Is there a question? Or? Yeah. Okay. So basically, this is my yeah. I think someone has their mic on. If you could just please mute it. Yeah.
Ma'am, I have a question.
Yes.
This model which I can see on the screen, where wages is dependent variable, the previous where
Yes,
wages
yes.
dependent variable, and education, experience, tenure, and female, all these are independent variables.
Yes, yes.
So in that case, female is measured on a nominal scale.
It is a binary variable. It's numeric. Yes, female is a
Then
yes.
that's non-metric. So that means in OLS, independent variable can be metric as well as can be non-metric.
I'm not sure what you mean by non-metric. This is a binary variable. So it is representing an ordinal variable, but it is basically, you know, it's taking a numeric value, 1 or 0.
So, yeah, but then that is taking numeric value, but that's not metric variable. No, it's not a ratio scale or an interval scale. It is a nominal scale. So can we take a independent variable on nominal scale?
Yeah, so nominal scale would actually, yeah, I mean, you know, you're just labeling these 1 or 0 because the additions and subtractions don't have any meaning. Yes, you can use these. Yes, it can be used. As long as they're numeric, this is called a dummy variable. It can be used in a multiple regression model.
When I was reading with about simple linear regression, one of assumptions of dependent and independent variables should be on a ratio scale.
Yes, but these dummy variables, this is an example of a dummy variable. They can be used in a multiple regression model as an independent variable.
Okay, ma'am. Thank you.
Yeah. Okay. So I'll talk about dummy variables in some more detail. Okay. Okay. So I hope the X matrix, what we are referring to the X matrix, I hope that is clear. So this is your X matrix, right? And the reason your X matrix, yes. The reason your X matrix has a column of 1s is because it's picking up your constant term. Now, what does this have to do with my assumption that there is no perfect correlation between any of the x's? You see, in case there is an exact relation between any of the two x's, then what's going to happen is that we can express one column in terms of the other. So if they're perfectly correlated, then it's something like x1 is equal to 2x2 or x1 is equal to 5x3, something like that. So two columns of your X matrix are going to become linearly dependent. Now, why would that be a problem? That will be a huge problem because you see the solution to my beta hat in matrix notation is the following thing. It is beta hat is equal to x prime x inverse into x prime y, where x is my X matrix and I'll have to be able to invert it. Now you see, if two columns of your X matrix become linearly dependent, then matrix inversion would fail because the determinant would go to 0, right? And in this case, you're not going to have an Ols estimator at all. So perfect collinearity has to be ruled out by assumption. Okay. So, you know, since we started 5 minutes late, can I take 5 more minutes before we take a break? Is that fine?
Yes, ma'am. Yes, ma'am.
Please go ahead.
So now, so I hope if this point is clear, and again, if you have a question, please you could ask. I'll just ask, you know, if you have your, please mute your mic, okay?
Co-host, please mute her.
Right. Okay. So now, right. So what I want to leave you with before the break is a difference between how you interpret the coefficient in a two-variable model versus how you interpret the coefficient in a multiple regression model. Now, if I have a two-variable model, right, then I simply say, so this is what I've done on my Stata screen also. I simply say that as education increases by 1 year, wages increase by just over 50 cents. Okay. That's all that you're able to say. Now, suppose you're running a multiple regression model. Suppose you're running this model. I'll just come to the question. That wages are being regressed on education, but along with that also on experience and tenure. Now, first of all, notice that the coefficient of education has changed. It's no longer 0.54, it's 0.59. And how do you interpret it? You say that as education increases by 1 year, wages increase by nearly 60 cents, 0.59, holding experience and tenure constant. So this is the big deal. Now you're saying that for two people with exactly the same number of years of experience and tenure, if one has an extra year of education, wages are going to be higher for that person by about 60 cents. So I just wanted to discuss this, that what is the meaning of holding other things constant? Okay, so what it means to hold other things constant. Yeah, I'm just trying to get this to go, but anyway, so what it means to hold other things constant can be understood if you do the following experiment, and I'll do it for you. Okay, so we have let's say a regressed wage on education and experience, suppose. Okay, and we are wondering that what it means to say education is that as education increases, wage increases by beta 1, holding experience constant. You see, if you were to run a regression of wage on experience, right? So you're regressing wage on the other variable, experience, and then you are getting the residuals. So what is the residual? The residual is the part of wage which experience does not explain, right? Now you're also running a regression of education on experience, and again you're taking the residuals. So now what have you done? You filtered out the effect of experience from both wage and from education, and you're using these residuals. So WR is the part of wage which is not affected by education experience, and this residuals, EduR, is a part of education which is not affected by experience. So you've gotten rid of experience from both these variables. Now when you regress WR on EduR, what you're going to get is beta 1. You're exactly going to get back this particular beta 1, showing you in what sense you're holding experience constant. You're filtering out the effect of experience from both variables every time you're running a multiple regression model. So it's a very powerful tool, because you see, you may not have any two people in your sample who have exactly the same number of years of experience and tenure. But if one has an extra year of education, you can say that for two people with the same number of years of experience and tenure, the one who has higher, an extra year of education will earn 60 cents more. Okay. So I thought maybe I could just run this regression and show it to you, but I, and if you want, I can do that, but no problem. That's okay, Shweta, no issues. I'm sorry. Yeah. Okay. All right. So shall we now take a short break and then come back after 10 minutes? Do you want me to kind of show this to you, and should I run the regression and show it to you, or is this something that seems plausible?
Ma'am, please run the regression.
Okay, sure. Okay, all right. So suppose I regress wages on education, experience, and tenure. Okay. Now note the coefficient of education here is 0.59. So now what am I going to do? I'm going to filter out the effect of experience and tenure from both, from wages as well as from education. So what will I do? I will regress wage on experience and tenure. So what I'm going to do is that I will regress wage on experience and tenure. Here goes. Now I'm not really interested in this. I'm interested in the residuals. So I'm going to call this WR, wage R, okay? Wage R. So what are these residuals? Wage R is a residual of the regression of wage on experience and tenure. It gives me that part of wage from which the effect of experience and tenure have been filtered out. Next, I'm going to run another regression. This time, I'm going to run a regression of one explanatory variable on the other two. I'm going to run a regression of education on experience and tenure. And again, I'm going to look at the residuals. So I'm now going to call this edu-R, and these are the residuals. Right. So now, why have we done all this? Because we want to understand in what sense we are holding experience and tenure constant. So please look at my original regression. Regression is a regression of wage on education, experience, and tenure, which gives me a coefficient of 0.59. What have I done to get this 0.59? I have regressed wage on experience and tenure, and I've got the residuals, right? I've called those residuals wage R. Next, I've regressed education on experience and tenure, and again, I've got the residuals. I'm calling these residuals edu-R. So now, when I regress wage R on edu-R, I should get back exactly the same coefficient, which is 0.5989. Okay, I should get back exactly this 0.5989651, which is what I got from my original equation of wage on education, experience, and tenure. So this 0.5989651 is exactly what I get when I run a regression of wage R on edu-R. So that's what your multiple regression is doing. So when you're interpreting this coefficient, be very mindful of the fact that it's giving you the effect of education on wage holding experience and tenure constant. Okay. Okay. So is there a question? Okay. Right. Okay. So maybe we can just regroup in 10 minutes. Is that okay?
Yes, ma'am.
Okay. So I think it's 6:40 by my watch. So I'll be back in 10 minutes. Okay. Right. Yeah, and if you have any questions, you please put it on and let me know, huh? Beginning of the next session. I'll be back in 10 minutes, please. Good evening.
Yes, ma'am.
Yes, can we start?
Yes, ma'am. Yes, ma'am.
Okay. Right. I'll just I will just share my screen. Okay.
Okay, ma'am.
It's saying that host disabled participant screen sharing.
Just a minute, ma'am. Just a minute. Please check, ma'am.
Okay, I'll just check. Yes, now I can share. Right. So if you have any questions regarding what I had covered so far, you could please ask at the beginning. All right. Now, okay, if there are no questions, what I will do is the following. I'll take you through certain issues that one is likely to face in multiple regression. Particularly the issue of multicollinearity, the problem of omitted variables bias, which are all very relevant problems. I'll touch on the problem of multicollinearity and just discuss why it's not something that you have to be really bothered with. And then just mention a few kinds of hypothesis tests that you can do when you have a multiple regression model. Mention because, you know, I don't really have the time to enter into the details. And finally, talk about a model with a dummy variable, what is a dummy variable trap, and then try to explain some results in models where you have dummy explanatory variables. So that's the plan. Okay, now let me start by flagging the following problem. You see, sometimes we are just interested in asking the following question. Is education important for wages? Does it matter if you know, if you are more educated? Are you likely to earn more? So all you are really interested in is the relation between wage and education. But then suppose the true model, suppose in reality wages are a function not just of education, but it also matters how many years of experience you have, how many years you've been in this particular company. Suppose these things are affecting wage, then even if you are interested only in education and the relation between wage and education, don't ignore the others. Don't ignore these other variables, okay? Because if you do, then you will be committing the mistake of getting a coefficient which suffers from omitted variables bias in the following sense. Please note that in this model, education has a coefficient of 0.59. Now, suppose, you know, I omit the variable tenure, right? Now, if I omit the variable tenure, why? Because I'm not interested in it. Then just see, instead of 0.59, education has a coefficient of 0.64. This is an example of what can happen when your model suffers from omitted variables bias. There's an upward bias, which is creeping out of the fact that it's very likely people who are more educated have spent more years with a certain company simply because they're able to retain their job. Okay, so here you are seeing that an extra year of education gives you a raise of nearly 70 cents, 64 cents, right? But that's an overestimation. Actually, it's less than 60 cents, right? So what's happening is that education in part is picking up the effect of tenure because education and tenure are correlated with each other. So what is it that's happening? You see, when you are ignoring certain variables which should find a place in your model, then you think your model is the following thing. You think your model is alpha plus, oops, just a second. Let's use the other pen. So you think your model is y is equal to alpha plus beta 1 x1 plus beta 2 x2, right? Plus u. That's what you think. But actually, what is happening? Actually, what you think is u contains beta 3x3. Okay, so it's actually beta 3x3 plus u, because whether you like it or not, your tenure is sitting. It's sitting in the errors. So what you think are the errors are actually not the errors, right? They actually contain x3. Now, why is this a problem? You see, if x1 and x2 are correlated, right? If x1 and x2 are correlated, then because the x3 is sitting in your errors, it's creating a correlation between the errors and the explanatory variables. And that's violating one of your model assumptions. And if this model assumption gets violated, then your coefficients are no longer going to be biased. They're no longer going to be unbiased. They are actually going to be biased. So this is a very, very sort of common problem and something we have to be really careful about. So this is particularly for all of you who are doing research. You may be interested in the effect of a single variable on y. But for heaven's sake, don't ignore the others, the other variables which are determining y. If they are correlated with your x, then they are all sitting in your errors and creating a problem of what we call endogenous regressors. So endogenous regressors occur when your errors are correlated with your regressors. And omitted variables is a ripe case for creating that kind of a problem. Okay. So, I mean, as you can see, the effect over here is to give you a higher coefficient on education. You're attributing more to education than is its due. So actually, education would be, just, as in the previous case we saw, education would actually account for less than 60 cents, but here, because it's also picking up the effect of the omitted variables tenure, because education and tenure are correlated, that's creating a problem. So this is one of the things that I wanted to flag, the problem of omitted variables bias and why we should be very careful about it. I hope this is clear. And if you have any questions related to omitted variables bias, you could please raise it now. Okay. Right. Okay. So now there's one other useful thing which I wanted to flag. If there are no questions on omitted variables bias, then let me just pass on and talk about this other sort of useful thing that that you can use whenever you're using a multiple regression model. These are called partial and semi-partial correlations. Okay, so what are these partial and semi-partial correlations? Let's look at partial correlations. I don't know if you can see there's a faint arrow. Now, when you're looking at the partial correlation between your dependent variable and the explanatory variables, then what is it that you're looking at? So let's look at the partial correlation of wage. So my model is the same. Wage is a function of education, experience, and tenure. And what is the partial correlation of wage with education tenure? Suppose you were to remove the effect of the other variables from both wage and education and look at the correlation between wage and education, right? So you are removing the effect of experience and tenure both from wages as well as from education, and then looking at the relation between wage and education. That's what the partial correlation coefficient is giving you, right? So this is simply the correlation between the part of wage, which is not related to either experience and tenure, and the part of education, which is not related to experience and tenure. And if you look at its square, so if you look at the square of the partial correlation, which is which is here, okay, partial correlation square, it's giving you it's giving you a kind of a R squared. It's giving you the percentage of variation in Y which is not associated with any other variable, neither education, experience, nor tenure, which is explained by x1. So so about 20% of the variation in wage unrelated to experience or tenure is explained by education. Okay, so this is, I mean, when you're looking at different models, you're not sure about the theoretical relation between variables. These are some of the things that you can actually look at. You can look at partial correlations. It'll give you some idea about how these variables are related with each other in isolation. Okay. Now, another very useful thing is the semi-partial correlation. Now, in semi-partial correlation, as the name suggests, what you're doing is you're removing the effect of x2 and x3 from x1, but not from y. So you have total y, and you have the part of x1 that's unrelated to x2 and x3. And you're looking at the correlation between y and x. So this is basically giving you what is the correlation between y and x alone. No other variable. Okay, that's what this 0.18 is. So sorry, that's what this is giving us. So the semi-partial correlation is this one. Okay, that's what this particular number is giving you. Okay, so if you were to look at the effect of wages, if you were to look at the correlation between education unrelated to experience and tenure and wages, right? It's explaining 42% of the variation. If you were to filter out the effect of experience and tenure from wages, then it would be actually explaining 45%. Now, what is the star piece in all of this? The star piece in all of this is really semi-partial, the square of your semi-partial correlation. Okay, you see, that gives the percentage of variation in y, which is explained only by x1 and x1 alone. Okay, and it gives you by how much your r square will decrease if you exclude x1 from your model, right? So basically, this is telling me that my r squared will decrease by 18 percentage points if I exclude education, and it is significant. So it's also giving you whether this decrease in r squared is significant or not. So if it has a very low p-value, that means it's significant. Okay. So both tenure is significant at 1%, as is education. So if I remove tenure, my r squared will decrease by about 8%. If I remove education, my r squared will decrease by about 18%. So we can actually try this out. You can just try this out. So in fact, I'll just do that for you. So if you look at a model where I am regressing wage on experience, education, and tenure, let's look at the r squared. The r squared is about 30%. So now, if I remove education, it should decrease by about 18, right? Yeah, so see, it's 12, okay? Just as the semi-partial correlation indicated, okay? So these are very useful things to be working with when you're playing around with models and you're wondering what happens if I remove this, what happens if I add that, and so on. So keep your partial correlations handy whenever you're looking at models. Okay. Now, this I'll quickly run over, telling you what's out there, sort of telling you what kind of hypothesis tests you can do in a multiple regression context, which involve more than one population parameter. We've already seen that if you have a multiple regression model, you can do a lot of hypothesis tests. A lot of hypothesis tests which are indicated by these t-stats and these p-values. All these tests involve a single parameter. So this t-stat is for the test on beta 1, this is for the test on beta 2, this is for the test on beta 3. But when you have a multiple regression model, you can actually do hypothesis tests which involve more than one population parameter. And let me take you through just a few of these as examples, as what you can do. Okay, so here we go. Okay. Right. Okay. Now, broadly, there are two kinds of tests. You can have tests which are of a linear combination of parameters. Now, what does that mean? It means, suppose this is my model, I can actually look at tests which link two or more of my parameters in a single equation like this. Okay. So I can test that beta 2 is equal to beta 3. Now here, I think one lady had a question that, you know, if they are in different units, I mean, how do I sort of kind of compare them and so on? You can always do a hypothesis test of this kind, okay? Where you're testing whether beta 2 is equal to beta 3, which means you're looking at this kind of a relation. Beta 2 minus beta 3 is equal to 0. Now, I don't know how many of you are economists, but if you are, then you would be very familiar with something we call the Cobb-Douglas production function, which is this kind of a production function that output is a function of technology, which is measured by A, labor measured by L, and K, which is capital. Now, if you have this sort of a function, then you can actually fit it in your Ols regression model by taking log of both sides, right? Now, once you've taken log of both sides, you may want to test this, that the coefficient of log alpha plus the coefficient of log beta is equal to 1. This is a test of what we economists call constant returns to scale. Okay, so here's another example where you can have a hypothesis test which involves a single linear combination of parameters. That is, it is involving some relation between the parameters. Okay, and just one equation. Yes. Yes. Did you want to say anything? Sorry, if you could just mute. If you don't have anything to say, it will disturb the others. Okay. Now, the other kind of test that you can do are what we call, well, they're actually called exclusion restrictions. Okay. Now, an exclusion restriction is when we say, suppose we were to drop x2 and x3 from this model, right? So, how do you do that sort of a test? You ask that let's test that beta 2 and beta 3 are together equal to 0. That's equivalent to saying, what if we were to drop x2 and x3 from the model? So do you see? These are multiple restrictions that you're placing on the parameters. And it's unlike something that you did in your two-variable model. In your two-variable model, you simply tested beta 2 is equal to 0, or you tested beta 3 is equal to 0. Now you can actually test that both beta 2 and beta 3 are together equal to 0. Now, one important test is actually your test of overall significance, where yeah, I think participant could please mute your mic. Yeah. So suppose I'm regressing y on 3 variables. Now, taken together, if I were to drop all 3, right? Now, I should actually be rejecting this null. I should be rejecting this null that together beta 1, beta 2, and beta 3 are equal to 0, right? So this is another test that we can do when we are using a multiple regression model. And this is not all, but we can test all kinds of things, such as, suppose I'm regressing y on x1, x2, and x3. I can test that beta 1 is equal to 1, beta 2 is equal to 0, and beta 3 is equal to 0 together, right? So where are these restrictions coming from? The restrictions will come from your underlying theory, okay? So the theory could be suggesting these restrictions, just like theory has suggested this particular test. So also, let's say there's some theory which asks for this test, then you can actually do that. Now, the broad thing to note over here is that these tests, the tests which involve a single linear combination, are t-tests, and these tests which involve multiple linear restrictions, these are all f-tests. So beyond this, in today's lecture, I don't really have the space to explain how these tests are carried out. But what I have done is I've actually done some of these tests, and I'll quickly take you through those. And if you have any questions, then you must please ask now, put it in the chat box or ask, okay? So I'll just take you through the tests that I have done. So here is my model. Wage is equal to education, experience, and tenure. And here I have tested that beta 2 is equal to beta 3. That is, the coefficient of experience and tenure are equal, right? So you can see experience has given a coefficient of 0.02 and tenure has 0.16. But looking at this, of course, I can't say anything because I know that this is sample specific. So I can't look at this and say that they are unequal, right? I need to do a hypothesis test so that I'm able to say something with some degree of probability. I can make a probability-based statement. So I look at this particular null, and well, this is a command in Stata which is going to do the test for you. But essentially, it's reported this t-statistic. And the t-statistic has a p-value of 0, which tells me that this null is getting rejected. So clearly, it's not the case that beta 2 is equal to beta 3. In fact, experience minus tenure is negative, which corroborates this fact that how many years you've been in a particular company has more effect on your wage than how many years of total experience you have. That's what this result is telling me. Okay, so this is one kind of a test of a single linear combination. Now, one of the reasons I wanted to bring this up here is I have seen students, researchers. Yes. Yeah, so I've seen lots of researchers who use multiple regression, but then they don't do these joint tests. They don't do these tests of linear combinations and so on, which could so easily be done with any package. I'm sure your SPSS will do it with great ease, right? Okay. Now, here I've just tested for the same model. For the same model, I've tested this particular null that beta 2 plus beta 3 is less than 0.6. So here I'm interested in this particular alternate hypothesis, right? So again, this is the Stata command. And here I'm just saying that together the effect of experience and tenure is actually less than is less than 0.6, right? I've just picked up that particular hypothesis. So again, this is getting rejected, and it's a t-test, right? So the null is getting rejected, which means that my alternate hypothesis is actually going through. Okay, so it's a left-tailed test in this case, and the coefficient lies sufficiently in the tails for rejecting the null. Okay. So that's one. Now another test that I had now is an example of a joint test involving multiple exclusion restrictions. So first of all, please notice that whenever you have a regression result, so this is a standard regression result, always the F test for overall significance will be reported. So this particular F value is giving you the test for the null hypothesis that together all your X variables don't matter, right? Together all the betas are 0. So you should be very keen to reject this null. And as you can see, it's 0.00. So I mean, this null is getting rejected soundly, which means that all my variables have a space in the model, right? So always the F test for overall significance is something that you should be checking. Now, another example of an exclusion restriction, I've simply tested that beta 2 is equal to 0 and beta 3 is equal to 0. So I've just tested that, and as I told you, this is a F test. So here also the p-value is 0 and the null is getting rejected. So it is not the case that beta 2 and beta 3 are together equal to 0. Okay, that's all I'm able to say on the basis of this particular F test. And finally, I have another, test of a general linear restriction. Why is it a general linear restriction? Because these are not exclusion restrictions. This is not just saying that it's equal to 0. So here I'm testing that beta 1 is equal to 0.3. I just picked up this value. And beta 3 is equal to 0. So together, it is the case that the sales elasticity of salary is 0.3, and that ROS does not have any effect on salary, right? That's what this is testing. Now, here you can see these are the two restrictions, and the F test is reported, and the F test has a very high p-value, right? So this p-value is 68%. So clearly, I can't reject this null. So I am going with this that yes, even though it's reported 0.28, I can safely say that beta 1 is equal to 0.3, and this is insignificant, and I can say that it's actually equal to 0. Okay, ROS has no impact on salary. So these are just some examples to kind of motivate you to also maybe in your own research contexts to take your multiple regression exercise forward and do some of these exercises because packages will execute it very quickly, and these are very simple to also understand. Please implement them. Okay, I'll be very happy if you do. Okay. Now, a problem that one faces when one is in the world of multiple regression, okay, is the problem of multicollinearity. And this is actually a little bit overhyped, not just little bit, it's quite overhyped. So first of all, what is multicollinearity? The first thing is that multicollinearity is very much a part of what we call the data generating process. So it's a part of life. We have to live with it, right? Now, please make a distinction between multicollinearity and perfect collinearity. Multicollinearity is not perfect collinearity. It simply means correlation between the explanatory variables, high degree of correlation between explanatory variables. It could be 0.99 or 0.99 or 0.97. That's multicollinearity. But perfect collinearity is when the relation is either 1 or -1. So when there's an exact relation between two variables. So please don't mix up the two, because perfect collinearity is ruled out by an assumption. Why I discussed that, right? You cannot invert your X matrix in the presence of perfect collinearity. So it's a very serious violation of your assumption, because your model can't even be estimated. But multicollinearity, as long as it is not perfect, does not violate any model assumption. There is no assumption which says that the x's should not be correlated with each other. Nothing in your OLS model says that. So even in the presence of multicollinearity, OLS estimators are blue. They're best linear unbiased. So, on that count, you need not worry. Now, how do you detect multicollinearity? We use something called variance inflation factors, right? So I'll just discuss those. And what is the problem? What is the problem if the model has multicollinearity? To see what the problem is, we have to look at the variance of the estimators. I already told you the estimators are random variables. They have distributions which have means and variances and so on. So that's where we have to look to see what problem multicollinearity creates. But before that, how to beat multicollinearity, because remember, we have to live with it. There's nothing that really we can do about it, right? We can't drop a variable simply because of multicollinearity, because then you're actually facing the bigger problem of omitted variables bias. Then you're actually getting biased coefficients, right? So you can't just drop a variable, okay? So we must try to have very large data sets. We must try to ensure that there's a lot of variance in our X variables. So for those of you who are planning primary surveys, please make sure that your explanatory variables have a lot of diversity. Then, it's one way you can keep the multicollinearity manageable. And sometimes, taking log or centering variables can help. When you take log, you're scaling down the variable, which brings down the variation, and sometimes that actually helps. And centering variables also helps at times, because so when you're centering a variable, you're really measuring the variable as a difference from its mean, right? So that also sometimes takes care of this problem. So let us see what problem it first causes. So you see, the variance of your beta hat, the variance of your estimators in a multiple regression model. So what is it that I'm talking about? This is what I'm talking about. So here I have a multiple regression model. So in this model, I have beta 1 hat, beta 2 hat, beta 3 hat, and these are the standard errors. These standard errors are nothing but it's like the standard deviation. So they're just the square root of the estimated variances. Okay, so that's what I mean. How are these standard errors calculated? There's a formula for them, right? You have to calculate the variance, and then you have to take a square root of the variance. So the formula for that variance of your estimators is this one. Okay, in a multiple regression model, the formula for the variance is the variance of beta hat j is sigma square upon SSTXJ into 1 minus R squared j. So what is variance of beta hat j? It's the variance of xj, which is your jth explanatory variable. SSTXJ is the total sample variation in that particular variable, the total sample variation in xj. And what is this R squared j? So R squared j is the R squared from regressing xj on all the other explanatory variables. So here you see where multicollinearity is coming in and creating a problem. Suppose there is a very high correlation between x and all the others, xj and all the others. Then this particular R squared, now mind you, this is the R squared from regressing this explanatory variable on all the other explanatory variables. Then this R squared will be very high. And if the R squared is very high, then that 1 minus R squared will be very low. And if 1 minus R squared is very low, that means the variance of beta hat is going to be very, very high. And if your variance of beta hat is very high, then what is the problem? Well, look, here is the problem. So remember your T statistic. Your T stat is nothing but the coefficient upon the standard error. So if you are coming out with a very high R squared and therefore very low 1 minus R squared and therefore very high variance, then the standard error will be very high, right? And your T stat is nothing but a coefficient by the standard error. So that means your T stat is going to be very, very low, okay? And your T stat will be pushed towards insignificance. It will be pushed close to 0 and your variable will become insignificant. So that is the problem that is caused by the presence of multicollinearity. Okay. If you have any questions on this, please ask. Right. So really the root of the problem is right here, and so is the solution. So you can see that if you have a lot of variation in your xj, which you will if you have a very large sample size. So if you have a large sample size, then this particular term is going to be very high, and that is going to bring your variance of the estimators down, irrespective of what is happening over here. So that's really the way to kind of take care of your multicollinearity. Keep large sample sizes, because if you do, then you're going to have a lot of variation in your x's, and that's going to save the day. So, right, this just spells it out. High correlation means R squared j is very high, which means this is low, and this then tends to be high, okay, which leads to high standard errors and low T stats, okay, right. So, you see, therefore, a natural measure of the extent of multicollinearity is something like this. Yeah, I'll just come to the question. You see, there's a question in the chat. I just come to it. So you see, 1 upon 1 minus R squared j is known as the variance inflation factor. The extent to which variance is higher because of correlation among the explanatory variables. Now, you see, if this is close to 1, if suppose, this is 0.9, indicating a very high correlation between x and the other variables, then this particular variable takes a value of 10, right? So just 1 minus 0.9, 0.1, and that's where you're getting this from. So it's just a kind of a cutoff, which we use as a rule of thumb, that 10 is like high because the correlation in this case is 0.9. Now, is it problematic? Whether it's problematic or not depends on how large a data set you have and how much variation in your variables is there. In other words, are the t-stats significant or not? So you can have significant t-stats, and there is no problem if there is multicollinearity in that case, right? So remember, with multicollinearity, as long as it's not perfect, the Ols estimators are blue. They're unbiased, they're best, and all of that. So there is really no problem. So basically, there is really no exact measure or cutoff for what is too high. So in practice, therefore, VIF has variance inflation factor is not a very, very relevant measure, but then it's there and one should know what it is. Okay, I see there's a question. Can you explain what is the basic difference between multicollinearity and perfect collinearity? Yes, sure. So you see, perfect collinearity is when R squared between two variables is either 1 or minus 1. So there's an exact relation. So you see it's a bit like this. You see if for every value of x1, let's say I have one value of x2, right? So then they kind of lie along this line. So for every x1, I have this x2. Every x1, I have this kind of an x2. So there's an exact relation between x1 and x2. Okay, then that's perfect collinearity, right? The correlation between these two is either 1 or it's minus 1. They exactly coincide with each other in that sense. For each one of this, I have exactly a particular value of that. Okay, but multicollinearity simply means that there is high correlation. It could be 0.90, 0.92, 0.93, but it's not 1, right? So that's the difference between perfect collinearity and multicollinearity. Okay, that's clear? Yeah. Okay, great. Okay, fine. So let us just carry on. Yeah. Okay, thanks. Fine. So having said all this, I have just given you an example of I've just given an example of what can happen when there is multicollinearity. So you see, if you have Stata has a lot of inbuilt data sets. So one of the inbuilt data sets that Stata has is called auto.dta. I'll quickly show you how to use that. So currently I have this wage data set that's loaded. Suppose I get rid of it from Stata's memory and I say use auto. Okay, sysuse auto. Right? Then it loads this data set, which has data on the make of, so it has data on 74 cars. What is the make, right? What is the price? What's the mileage? What is the repair record? And several features of those 74 cars, like weight, length, and all that. Okay, so this is a data set that I have used for this particular example. So I have regressed mileage on price and few other features, including weight and length. So you see, when I put in both weight and length, the variable weight is statistically insignificant, right? It has a p-value of 45%. So clear insignificant. Okay. Now, you see, weight and length are kind of related. And when I sort of throw out length, right, I see that weight has become significant, very, very significant now, right? So this is exactly the problem that multicollinearity causes. So if you're facing this kind of a problem, you sort of remove one variable or you add some observations and suddenly what was significant is becoming insignificant and so on, then that's a clear sign that that's the presence of multicollinearity. Okay. And once you drop weight, you can see that length is significant, and that's another sort of sign that the two of them are correlated. However, if weight and length are both important, then if you're dropping one of them, then you're having serious omitted variables bias, because they are highly correlated and this variable is sitting in the errors, and that's that's going to give you biased coefficients. So in other words, if you were to look at my original data set, then weight has very low coefficients, 0.001, and length has 0.13, right? Now, if I'm dropping all these things, then you can see that the coefficient of length is actually increasing to 0.17. So then you end up attributing more to the length of the card than you should be doing. So there is this problem of bias. So I mean, there is no easy solution really, because if you drop the variable, then there's a problem of bias and you're violating the assumptions. Whereas if you don't, then you're not getting a significant coefficient. Now, this is the perfect place where you use joint tests. You use joint tests to see whether you should be dropping both of them. You see whether their coefficients are adding up to something that they should be adding up to if it were significant. And just think of creative ways of overcoming this problem. There is no easy solution that if there's multicollinearity, you do that. But what I want to warn you is dropping the variable is something you should be very, very careful about, because at least with multicollinearity, your estimators are blue. But if you drop them, then they're not. And you're losing the basic property. You're losing the basic property of unbiasedness, and your regressors are becoming endogenous. They're becoming correlated with the errors. Okay, so that's a serious problem. Now, here I've calculated some variance in patient factors. Again, this is done using Stata. And you can see that the VIF of weight and length are actually higher than 10. They're 11 and 13, indicating that there is this extent of high correlation between these two variables. Okay, so that's something to note. Okay, right. So now I can talk about dummy variables and models with dummy variables. And right, so we'll start with what are dummy variables. Okay, so they're variables which take only two values, and those two values, I mean, you can call it anything and anything, but it's most convenient to have 0 and 1. Okay, so this is a convention which we follow, and the two values are 1 and 0. Now, where do we use them? As one of you had mentioned earlier, so sometimes, we have all these nominal characteristics of the data, right? Like marital status, gender, educational qualification, occupation. These are all features of the data, and these are variables which are nominal variables. So they cannot be directly used in a regression. But we can actually use dummy variables to quantify them. And that's something that we use a lot of times, okay? So these nominal variables, mind you, are identifying groups in the data, right? So to that extent, the dummy variables are very useful because they're helping us to combine these different groups into a single large database, and yet they are going to help us identify the coefficients separately for each group, right? So if I have men and women, married and unmarried, educated and uneducated, we can actually sort of identify the coefficients separately for each of these categories, even as we use dummies to estimate a single regression involving all of these variables, okay? So let's look at some examples. So again, here I have a data set which has wages, education, years of experience, age, and I have a variable called gender, which gives the gender of the person, and a variable called race, which mentions whether the person is white or non-white. So you can tell that this is example from pertaining to the Western European countries, American countries, and so on. So here I define a variable called male, which takes the value 1 if the observation belongs to a male, it pertains to a male, and it takes 0 otherwise. Okay, this is an example of a dummy, right? And typically I'll name the variable for whichever category it takes the value 1. That's the convention that one uses because it's useful. It helps you remember what that variable represents. I mean, what is 1 and what is 0. So for instance, white takes the value 1 for whites and is 0 otherwise. Okay, non-whites is 0 and for whites it's 1. Right? So this is literally what a dummy variable is, and I hope it is clear. Right. Now, you know, sometimes you actually have more than one category. Yeah. You have more than one category in the data, and not just 2. So earlier, you know, I just showed you male, female, white, non-white, and you have 1, 0. But sometimes you can have a problem like this, where you have data on sales, you have data on advertisements. Both of these are in millions of dollars, and you have which quarter the sales took place in. So quarter 1, quarter 3, quarter 2, or quarter 4, right? So again, a nominal variable. It just tells you in which quarter the sales occurred. So here I have 4 categories, right? 4 groups. Quarter 1, quarter 2, quarter 3, and quarter 4, right? So how do I turn these into dummies? Well, I simply define 4 dummies. So look at my dummy Q1. It's 1 if the variable is, if the sales are in quarter 1, it's 0 otherwise. Q2 is 1 if it's a sale in quarter 2, 0 otherwise. Q3 similarly is 1 if it's, you know, pertains to a sale in quarter 3, 0 otherwise. And so on for Q4, okay? So I hope this is clear, that if you have 2 groups, as you saw in this case, I just have 2 groups in the data, male and female, then I can have 1 dummy does the work. If you have, you know, race, again 2 groups, 1 dummy does the job. But if you have something which has 4 groups, then you can actually define 4 dummies, and we'll see, we'll use any 3 of them. Okay, why? We'll just see that in a bit. Okay. So here I'm talking about models which will include dummy variables as explanatory variables. Okay, so models with dummy explanatory variables. Okay. So, yes.
Ma'am, I have a question.
Yes.
The example which you gave, quarter 1, quarter 2, quarter 3.
Yeah.
Can that not be a panel data regression? How it is different from panel?
No. This is not a panel. This is a cross section. So it's it could be a time series also. It could be a time series or a cross section, but it's not a panel.
Time series, yeah. I mean, time series and panel, wherein we are getting a data for over a period of time, quarter 1, quarter 2, quarter 3. I'm a little confused with that.
Yeah, I see. So you see, suppose this is for a cross section. So I have data for 100 firms. Let's say 100 firms which are selling FMCG products. Okay. So for firm 1, I have that it sold $20 million and it spent $3 million in advertisement, and the sale happened in quarter 1. Do you see? Firm 2, it sold $35 million, spent $5 million, and that sale happened in quarter 3. Okay?
Understood.
Yeah.
Thank you, ma'am.
So, yeah, sure. So, right, a panel and a time series are slightly different. If I have the time at the end, we can come to that. Okay. Right. So here, one thing is that, you know, you name dummy variables by whichever category you have plugged as 1. It helps just to remember, rather than calling it gender or ethnicity or marital status. If you name it married or unmarried, then you just remember what happens. Okay. I mean, for which is a category for which it is 1, because that has a very important bearing on how you interpret it. Now, please realize what happens if you add the dummies for all the groups. Okay, so let's see that. So here I have two groups in the data, female and male. I have two races, white and non-white, and I have defined two dummies, male and female. Let's take this first, okay? So I have two groups in the data and I've got two dummies. Now what happens if I add these two dummies? Yes, tell me. What will I get? Come on.
One for all the values.
Yes, I'll get one for all the, I'll get a column of ones, basically. Okay, so you see, therefore, I mean, this is problematic because you see, if you get a column of ones, I'll quickly take you back to your X matrix. Remember, this is a multiple variable, multiple regression model, and you have your data in the form of an X matrix like this. Okay, so look at this. So if I have both my male and my female dummies in the same model, then together they're adding up to one. Then what will happen? Two columns will add up to a third column. And the assumption that the columns are linearly independent, that assumption will fail and I'll have linear dependence. So I'm going to have I'm going to have a perfect relation between three of the columns, two of them add up to a third. Now, why do I have this column of ones in the first place? Because my model has a constant term. So that's the basic problem of what we call the dummy variable trap. If your model has a constant term, then you must never have as many dummies as you have groups. You always have one dummy less than the number of groups you have. So if there are two groups, you have one dummy. If there are four groups, you have three dummies. That's the rule. Okay. So I hope the dummy variable trap, what it is clear. If it is not, you can please ask. Okay. I mean, if there's a question, you can please raise it now. Any question about the dummy variable trap? Right. So basically, therefore, when my model has an intercept term, I will always use one dummy less than the number of groups, right? So for male, female, I only use female. For married, unmarried, I'll only use unmarried. And I'll only use three dummies in a 4-quarter case, okay? Otherwise, we land into a dummy variable trap. Now, remember, if your model does not have a constant term, in that case, what do you do? In that case, you can have as many dummies as you have groups, but it is not a good idea to drop a constant in a model, okay? So always keep the constant term there. Even if the constant term is insignificant, keep it in, because when you're dropping a constant term, you're moving from a case of unconstrained OLS to constrained OLS, a case where the constant is becoming 0. So that's not always a nice thing to do for certain reasons. So keep the constant there until unless you have a very specific reason for removing it, and avoid the dummy variable trap. Okay, so now we move to a case where we have a model with a single dummy variable. Okay. Now, what's my aim over here? My aim over here is to help you, or rather to sort of take you through the steps of how to interpret the coefficient of the dummy when your model has a dummy variable. In other words, before I come to all of this, let me show you this. Okay. So look at this regression where I'm regressing wage on education, experience, tenure, and male. So male is a dummy variable. Now, so far I've been talking about how you interpret the coefficient of education, how you interpret the coefficient of experience, and so on, holding other things constant. Now my focus is that given that the dummy variable is a special kind of a variable, it's a 0-1 variable, is there any difference in how we interpret the coefficient of the dummy? What does the coefficient of the dummy represent? Is there anything different about the way we interpret it? And there is some difference. So that's what I'm going to come down to. And that's what we are going to try and understand using the theory. Okay. So that's the point. Okay. So look at my model here. I'm regressing y on x1 and male. Okay, so I'm just keeping it simple. One variable and one dummy variable. Okay, this is x1 is our normal variable and male is a dummy variable. Now, male takes two values. Male takes the value 1 and male takes the value 0. So let me write my model in each case. Now remember, I can write my model as the average value of y given x1, which is exactly what I've done over here. So the average value of y given x1 and, well, x2 is male, and given that male is equal to 1. So when male is equal to 1, this variable takes the value 1, so that my model simply boils down to beta naught plus beta 1 x1 plus delta. Delta is just a constant. So in other words, this is what my model boils down to. Is the average value of y given x1 and male equal to 1. So clearly you can see that the intercept term when male is equal to 1 is beta naught plus delta plus beta 1 x1, where delta is the coefficient of my male dummy. So, you know, if you have any questions on what I'm discussing now, you can please put it in the chat box or ask. Okay, right. Now, what is the other variable that value that male can take? It can take the value 0. So the average value of y given x1 when male is equal to 0, well, in that case, this term just disappears, right? This delta term just disappears. So it's just beta naught plus beta 1 x1. So you see, there's a couple of things I want you to note over here. When you're using a dummy variable called male, you are literally saying that I'm estimating two lines between, let's say this is wage and this is education. I'm actually estimating two lines between wage and education, one for males and one for females. And how are those lines different? They're different in terms of this delta. And what is that delta? The delta is the intercept. Okay. So you're saying that the male line is beta naught plus delta, and the female line is simply beta naught. Delta may be positive or negative, and depending on that, the intercept is either going to be higher or lower. Okay, so that's the first thing that I'd like you to note. That when you are actually estimating a model where you're regressing a dependent variable on an explanatory variable and a dummy, you're actually allowing for two lines which have the same slope. The slope is the same. The slope is beta 1, right? But the intercepts are different. The intercept in this case, you see they are using the female dummy. So the intercept is beta naught plus delta naught for females. Okay. So this is the intercept for women. And this is the intercept for men. Okay. So, so you see in this case, delta naught is negative, which is why the line is below it. But basically, beta naught plus beta 1 education is the line for men. All right. So we call the left out group is known as the base group. So in this regression, male is the base group, whereas in the regression that I have run, female is the base group. Okay. But the basic point that I want you to get is when you have a model with a single dummy, it's also called an intercept dummy. You're essentially allowing for two different regression lines which have the same slope, but which have different intercepts. So that's the first thing, just the graph, and in terms of the graph, what it means, what it means to be using a single dummy variable. And now how do you interpret it? So you see I have all these equations written over here, and let me just get rid of all this stuff so that it's clear. So if you look at equation 2, this is average wage of a male. And if you look at equation 3, then this is the average wage of a female, because male is equal to 0 in this case. Just subtract 3 from 2. Okay, so equation 2 minus equation 3 is your delta. So delta is giving you the difference in the average wage of a male minus the average wage of a female. Okay, so that's, I mean, apart from all these lines and everything, I mean, this is really what you're after. So when you have regressed a model on a dummy variable, the coefficient of the dummy is giving you the difference in the average y for the dummy group, the group for which it's taking the value 1, minus the base group, the dummy that you've left out, or the category for which it's taking the value 0. Okay. So now let's see some results, and if you have any questions, you can please raise it. Right. So, well, here is one case which you can see. I have just written this in equation form, right? So I have just taken the numbers and written it out. So here 1.81 is the coefficient of the dummy. This is my delta. Now, how do I interpret this? So here I'm just assuming that wages are measured in hundreds of dollars. Okay, just a small assumption. So here we are saying that for a male and female with the same years of education, experience, and tenure, that is holding education, experience, and tenure constant, the average wage of the male would be about $180 more than the female average wage. Why? Because I've assumed that wages are in hundreds of dollars. So it's 1.8 into 100. Okay. So this is telling you that if you find two people who have absolutely the same number of years of education, experience, and tenure, if the person was a male, then that person gets a higher wage, higher by $180, because this coefficient delta is actually statistically very, very significant. Okay. So that's how you would experience that. That's how you would explain the and interpret the coefficient of a dummy variable. Now, what I've done is I've just done two very small exercises. One is, instead of a male dummy, I've taken a female dummy. Can you quickly tell me, same model, if I substitute female with male, sorry, if I substitute male with female, what should I see? Same thing. Male is 1.8. What should the female coefficient be? It should be minus 1.8.
Yes, minus 1.
Yeah, so that's exactly what you see. Okay. So if I instead of male, if I were to put in female, that's exactly what you see. So that's one small exercise. And the second one which I did was, the dummy variable trap. So you see, if you put in both the dummies in this model, which has a constant term, then one of them is going to be omitted because of collinearity. So in this case, whatever you put in second gets omitted. So here, female is retained and male is getting omitted. This is just an example of what happens when you're in the dummy variable trap. Okay. Okay. Now, I just had one other sort of exercise where I have my dependent variable as in log form. Now, if your dependent variable is in log form, then your coefficients have a percentage interpretation. Okay, so this literally means that for an extra year of education, okay, the wages are going to increase by 8.7%. Right? That's what this means. So the coefficient times 100 gives you the percentage change in the dependent variable. So the coefficient of female is no exception. The coefficient of female over here is minus 0.3, right? So this is telling you that, a female with the same years of education, experience, and tenure as a male earns about 30% less on average. Okay, so that's something that I just wanted to flag when you have a model with a log dependent variable. Okay, right. Now, if you have a model with multiple dummy variables, then also the coefficient, the interpretation of the coefficient does not change. So here you see, I have Q1, Q2, and Q3. So my base group is Q4. Okay. So what does that mean? it means that each of this delta 1, delta 2, and delta 3, they're giving the difference in average sales. Okay, so it's the same amount of advertisement expenditure. It's giving me the difference in average sales between quarter 1 and quarter 4, quarter 2 and quarter 4, quarter 3 and quarter 4, because my base group is quarter 4. Okay, so the coefficient of the dummy is always giving me the difference in the average of the dummy group with the base group. Okay, so if you want to change the base group, then what do you do? Well, if you want to change the base group, then you simply use the other you simply sort of I mean, here I just sort of explain the same thing, so nothing much to do over there. But if you want to make quarter 1 your base group, then you simply estimate this model. So in this model, quarter 1 is the base group. So here delta 1 will give me the difference between quarter 4 and quarter 1. Delta 2 will give me the difference between quarter 2 and quarter 1, quarter 3 and quarter 1, and so on. Okay. So that's something that I wanted to discuss so far as the coefficient of a dummy variable is concerned, when you simply have an intercept dummy in the model. Okay. Right. Now you can also have a model with intercept as well as slope dummies. Now, what is a slope dummy? First of all, you can have these sorts of situations, right? These sorts of situations where you are not constraining the two regression lines to have the same slope. You're allowing them to have completely different slopes and different intercepts, right? As in this case. How do you accommodate this? Well, you accommodate this by in the following way. So suppose you have a model like this, okay, where you have a dummy such as female, right? And what you do is you also interact or you multiply the dummy with your X variable, okay? So here, what I'm doing is I'm allowing the model to not just have a different intercept, so that the male and the female regression lines do not just have different intercepts, but they also have different slopes. And the way to accommodate that is to include the dummy and also multiply the dummy with your explanatory variable. So if you were to just write it out, for the two categories, female is equal to 1 versus female is equal to 0, you'll see that for female equal to 0, that is the average regression line for men, it's just beta naught plus beta 1 x1. Whereas if you look at the term female is equal to 1, then you'll see that both the intercept is now beta naught plus delta naught and the slope is beta 1 plus delta 1 by just plugging in female equal to 1 and then working out this model. Okay. So here you see the average wage would be same for men and women only when both the coefficient of the dummy as well as the coefficient of the dummy interaction are together equal to 0. It's only then when the two groups would have the same line. Okay. So what's the basic takeaway? Because I realize it's kind of end of the day and all that. So the basic takeaway is that if you have a model with a dummy variable, number 1, avoid the dummy variable trap. Number 2, realize that there are two kinds of models you can write. You can write a model which has a simple interaction, a simple intercept dummy, which is you're just regressing on x's and one dummy, right? That's one kind of model you have, which is this sort of a model, right? Okay. I just have in this model explanatory variables and a dummy. Please realize that when you're doing this, the coefficient of the dummy is measuring the difference in the average between the dummy group and the base group. And essentially what you're doing is you're allowing for two lines which have the same slope, but which have different intercepts. That's the first thing. What's the second thing? The second thing is that you can have another kind of model. You can have another kind of model where you're allowing for a more general possibility. You're now allowing for the possibility of the two lines to not just have the same, to not just have different intercepts, but to also have different slopes. How do you achieve this? You see, you achieve this in reality, or you achieve this in practice in the following way. So remember my model. My model is wage is regressed on education, experience, and tenure. Now I want to allow for two completely different lines for the men and the women in my data set. So what do? I include a female dummy. On top of that, I multiply the dummy with each one of my explanatory variables. I multiply it with education. I create a variable called FED, which is female into education. I multiply the dummy with experience. I generate a variable called FX, which is female into experience, and F10 is female into tenure. And now look at my model. So you see, here I have a model which allows for completely different regression functions, that is different slopes and different intercepts for men and women. And what do I have on my model? I'm regressing the log of wage on education, experience, tenure, as I was doing earlier. But now I have a female dummy, plus I have female into education, female into experience, and female into tenure. So when you are interacting your dummy with each and every explanatory variable, you're essentially allowing for completely different regression functions for the two groups which are there in your data. And this allows you to do a chow test. So that's the last thing I'll cover now. So a chow test is basically a test where you're doing a joint test that together all the dummy, the intercept dummy and the slope dummy. So when you're multiplying female into education or female into experience or female into tenure, you are generating what are known as slope dummies. And this is called an intercept dummy. Female is just an intercept dummy, right? So when you are testing that all the dummy coefficients are together equal to 0, you're basically testing that the two regression lines are essentially the same. So this null is the null that the two regression lines are the same. Because if all the dummies are 0, then there's basically one regression line. If all the coefficients are essentially the same, right? If they're together equal to 0. Okay. So sorry, not the same, but if they're all, I mean, they are the same, but the same is 0. If they're all the dummies and the interactions are 0, then there's just one line, right? And this is known as a chow test. This is a chow test for a cross-section model, okay, which you're allowing for the fact that two completely different regression lines, but then you just are running one regression, and then you're taking all the variables and testing that they're jointly 0. So here it's just getting rejected. The test, it's a F test, and the p-value is 0, so the null is getting rejected. And if you want to simply test that, okay, maybe the slopes are all equal. So maybe the coefficient of female into education, female into experience, female into tenure, maybe all of those are equal to 0. That is, all the lines have the same different intercepts, but they have the same slope. You can also test that. Here, you're just testing that the slope dummies are equal to 0. And in this case, again, that null is getting rejected. So indeed, there is this chow test is providing evidence that you have two completely different regression lines with different slopes and different intercepts. Okay, right. So I think it's 8:05, so I'm the time is up. So if you have any questions, I'll be happy to take them, please. If you have anything and any queries or anything pertaining to what I had mentioned. No? Okay. Right.
Maybe, ma'am, which is mentioned in the chat box, can you just, you have to visualize?
Sorry.
Maybe 1 and 2 question which is mentioned in the chat box.
Okay. Yeah, I think I have answered all the questions in the chat
Okay,
box.
okay.
Yeah, because there somebody has asked whether what's the difference between multicollinearity and perfect collinearity. That I have answered. Okay.
Okay.
Yeah.
Okay, ma'am.
Okay.
Just give me a second, ma'am.
Yeah, sure.
So I proposed a vote of thanks.
Okay. You can share the data set. Yeah, I'll share the data set with the. I will share the data set with the organizers, and they'll share it.
Okay,
Thank you.
Okay.
Yeah.
So it has been such an honor to be part of this FDP program. On behalf of the TLC Ramanujan College and Indian Accounting Association NCR chapter, I would like to extend my heartfelt gratitude to our esteemed guest, Professor Ananya Ghosh Dasidar. Your lecture, Multiple Regression and Various Model, was very enriching and interesting. I am sure it must have added to the knowledge of our participant. You have presented your lecture by involving the participant all along the lecture. The participants were also equally enthusiastic in responding to your queries. I would like to thank all of you present here in this virtual platform. Thank you and all. Thank you, ma'am.
Thank you very much. I think the best thing for anybody who's teaching is to have an audience who are actually asking questions and responding. So thank you for being such a wonderful audience. Thank you very much.
Thank you, ma'am.